Hello and welcome to the short video, Carbohydrate Digestion, Absorption, and Transport. This is Instructor Parrish. In this short video, we're going to do just as the title states. We're going to discuss the digestion, absorption, and transport of carbohydrates throughout the GI tract. To start off, let's first take a look at carbohydrate digestion. The goal of carbohydrate digestion is to break down all of the carbohydrates from our diet into absorbable units. The only way carbohydrates can be absorbed in the GI tract is in the form of monosaccharides, or single carbohydrate units. So therefore, throughout the GI tract, we need to gradually start breaking down the disaccharides into single monosaccharides and the polysaccharides into single monosaccharides. This will happen using hydrolysis reactions. In a hydrolysis reaction, a water molecule will donate a hydrogen to one of the monosaccharides and a hydroxyl group, or an oxygen and a hydrogen, to another monosaccharide. By making these donations, the monosaccharides are able to split apart, resulting in two separate monosaccharides, or two separate absorbable units. These hydrolysis reactions will occur anywhere in the GI tract where digestion occurs. Now let's start out with the mouth. In the mouth, carbohydrate digestion begins. And the enzyme which is present in the mouth is salivary amylase. And salivary amylase is going to begin starch digestion. Starch will be partially broken down into shorter chains of glucose molecules. Okay, so there can be shorter polysaccharide chains, and then also the starch can be broken down into maltose, which is a disaccharide consisting of two glucose units. Okay. There is very minimal absorption of carbohydrates in the mouth. So typically we say there's no carbohydrate absorption occurring in the mouth, but there may be minimal amounts. Okay. All right, now let's move on to the stomach. In the stomach, salivary amylase is deactivated by the hydrochloric acid present. So salivary amylase is pH sensitive. So the very low pH within the stomach deactivates this enzyme. There are no carbohydrate enzymes present in the stomach, and so really digestion of carbohydrates by enzyme stops in the stomach. Now the hydrochloric acid that is present in the stomach does help to weaken some of those bonds between the monosaccharides that are present within the disaccharides and the polysaccharides. So minimal digestion does occur. Now the soluble fibers that are present in the stomach actually help to delay gastric emptying, and this promotes satiety, or it helps you feel satisfied between meals. It helps you feel satisfied longer. And then insoluble fiber provides bulk, and it promotes the feeling of fullness. So it helps you feel full so you stop eating sooner. And then there is no carbohydrate absorption occurring in the stomach. Now let's move on to the small intestine. In the small intestine, this is the primary site of carbohydrate digestion and absorption. Okay? Within the small intestine, there's first pancreatic amylase. And pancreatic amylase is secreted within the pancreatic juices. Pancreatic amylase will finish off starch digestion. Okay? So we'll break all of those polysaccharides or glucose chains into smaller chains and eventually into only glucose and glucose units, which we call maltose. And then the intestinal enzymes, or enzymes that are present on the right outside the intestinal cells within the villi and microvilli, those are actually going to digest the disaccharides. So maltase will break down maltose into single glucose molecules. Sucrase is specific to only sucrose, and sucrase will break down sucrose into individual glucose and fructose units. And then lastly, lactase is specific to lactose and will break down lactose into glucose and galactose units. The end result will be mostly all glucose because glucose makes up all of these disaccharides. It makes up all of the polysaccharides and can be present by itself within the food that we consume. And then there will also be some galactose and fructose present. Now, in the small intestine, this is where carbohydrate absorption will occur. Only monosaccharides will be absorbed into the intestinal cells. So disaccharides and polysaccharides will not be absorbed. Only monosaccharides. And remember, the monosaccharides that can be absorbed are glucose, fructose, and galactose. Once these are absorbed into the intestinal cells, they'll then be released into the bloodstream. They can be used for immediate energy by the cells within our body. They can be stored as energy, or for instance, the fructose and galactose will be eventually converted into glucose to be used as energy or stored as energy within the body. You'll learn about this more so later, whether it be in class, another video, or by reading it in the textbook. All right, so the end result of carbohydrate digestion will be the absorption of the monosaccharides glucose, galactose, and fructose in the small intestine. Now, let's take a look at what happens with soluble fiber in the small intestine. Now remember, soluble fiber and insoluble fiber are not digested by the enzymes within the GI tract. Okay, they're not digested, so therefore they cannot be absorbed. Soluble fiber actually has some important actions within the small intestine. Soluble fiber can actually bind to bile, which is used to digest fat, and is also made of cholesterol. And it can bind to cholesterol that is in the GI tract from our diet. So what it can do is it can attract to the bile and attract to the dietary cholesterol and pull it through the GI tract so that it's not absorbed in the small intestine. Instead, it's pulled through and into the large intestine and eventually excreted. Okay? By reducing the amount of bile that is reabsorbed, because bile is made of cholesterol, and also reducing the amount of cholesterol or dietary cholesterol that is absorbed in the small intestine, we are thereby lowering our risk for heart disease. And then the other function of soluble fiber in the small intestine is to delay the absorption of the monosaccharides. By delaying the absorption and promoting a more gradual absorption of monosaccharides in the small intestine, we're going to promote a gradual rise in blood glucose levels. And this is very important in blood glucose management, especially for individuals who would have diabetes. And again, you'll learn more about this either in another video, in class, or by reading the textbook. Now let's move on to the large intestine, and let's look at what happens here. In the large intestine, all of the absorbable carbohydrates have already been absorbed. So there's really no carbohydrate absorption that is going to occur in the large intestine. Now, soluble fiber will be digested in the large intestine by the bacteria or the normal flora that is present, but it will not be digested by enzymes. Okay, so the soluble fiber can be digested by the bacteria, the healthy bacteria that's present in the large intestine. By digesting the soluble fiber, this provides energy to the bacteria to help maintain that normal flora population, and also provides energy to our colon cells. So it promotes health of those colon cells. In addition, by providing energy and helping to digest some of the soluble fiber, the pH of the intestinal juices within the large intestine are going to be altered. And this can help, one, reduce inflammation, and also can activate cancer-killing enzymes within the large intestine. Okay? So by reducing inflammation and then also by activating cancer-killing enzymes, we can reduce one's risk for colon cancer. Next, soluble fiber can bind to cancer-causing agents and toxins that can be consumed with our food. And so by binding to these cancer-causing agents and toxins, we're able to pull those through the large intestine before they can cause any harm or cause cells to become abnormal within the large intestine. Lastly, soluble fiber softens the stools. And so by softening the stools, soluble fiber helps to reduce the pressure on the vessel walls. This helps to reduce one's risk for hemorrhoids and also reduce one's risk for constipation. Now let's take a look at insoluble fiber. You're going to see that insoluble fiber and soluble fiber work together in many ways to help promote health. Although insoluble fiber is not able to be digested by the bacteria in the large intestine, it passes through the large intestine and is excreted as is. So there is no digestion of insoluble fiber. But it does add bulk to the stool, and by adding bulk, it makes the feces less dense and hard. So that reduces the pressure on the colon walls, which can additionally help reduce one's risk for hemorrhoids. Insoluble fiber also promotes gut motility, so that reduces one's risk for constipation. Okay, it keeps the feces moving within the digested material moving within the large intestine, so their blockages do not form. Next, it also speeds the passage of those cancer-causing agents and toxins through the large intestine. So there's less time for those agents or toxins to cause to react with the colon cells and promote cancer. And then lastly, insoluble fiber stimulates the muscles and walls of the colon, and by stimulating the muscles and walls of the colon, they become stronger and less likely for pockets or pouches to form, which could cause diverticulosis. Okay? So insoluble fiber can thereby help reduce one's risk for diverticulosis. All right, now I want to show you a figure I want to point out. This is a figure 4-8. This is in chapter 4 of your textbook. If you have an older edition of textbook, it might be figure 4-10, but in the current edition, it's figure 4-8. This is a wonderful review of what I have discussed in the video, or at least most of what I've discussed in this video. So you might want to take a look at this, and this can be a little summary or review for you. Thank you for watching this video. As always, please feel free to contact your instructor with any questions regarding what you learned in this video. Bye-bye.